Hi, my name is Kevin. This is my first time speaking at RailsConf. I'm really excited to attend conferences in person again. I think the RailsConf staff have done a fantastic job of making this happen while making sure everyone stays safe. A bit about myself, I work at Shopify. I just had my 1-year anniversary there. I still think it's a fun place to be. We do really interesting work. You probably heard, but we're hiring basically all the time. So feel free to reach out if it's interesting to you, or we have a booth in the sponsor area. You can talk to someone. In particular, I work in a group called the Ruby on Rails Infrastructure Team, and this is a group that's basically tasked with ensuring the longevity of the Ruby tools we use at Shopify. So that can take shape in terms of performance, or correctness, or ease of use. We kind of tackle everything. So we have people working on type systems, working on the developer experience and trying to make tools like Visual Studio Code work better for Ruby development. We also work on optimizing compilers for Ruby. There's a lot there, and if you use Ruby open source stuff, there's a pretty good chance that you've used work that has come out of that group. In particular, I work on a team working on a project called Truffle Ruby. Truffle Ruby is a completely new implementation of Ruby with a strong emphasis on peak performance. In particular, we're looking to optimize Ruby the way Rubyists actually write it. In contrast, sometimes when there's these sorts of alternate implementations, they ask you to change the way you write code to optimize for the tool, kind of like ASM.js did. So we look at things like metaprogramming and try to find out how we can make that work just as quickly as if you called methods directly instead of using method missing and things like that. Our goal is to make it like 100% compatible with MRI. We even run native extensions. We're still working on getting there. But to give you an idea of what we're looking at, here's 2 benchmarks that come out of a project called YJIT Bench. This is actually from the YJIT team. And both of these are intended to look at subcomponents of Rails. So we have on the left a benchmark using Active Record, and on the right one using the default templating engine. And Truffle Ruby is the one all the way on the right. So for Active Record, we run about 4.5 times faster than CRuby 3.1 does on this benchmark. I picked this one because I think it's a little interesting when we talk about like Active Record. I think a lot of people think, well, there's a database involved, there's going to be a lot of I/O, so our performance is completely gated on the I/O, or how quickly the database can respond. But there's actually a lot that can be optimized within the Ruby VM as well. And we're not talking like 10 or 15% incremental improvement. This is like 400 to 500%. All right, so getting to the talk. Title is Service Denied, Understanding How Regex DoS Attacks Work. There's a lot to try to work out to do this in a 30-minute block, so I'm going to try to blitz through some stuff here. First, I want to establish the context for it, then explain what denial of service attacks are in case you don't know, then specifically what regular expression denial of service attacks are. And to understand that, we need to do like a crash course in performance analysis. So this is like big O notation, if you haven't heard of that before. And then what a regular expression engine actually does. And then hopefully this all comes together in the end into like some kind of cohesive idea. All right, so context. Looking at 2021, there was a rapid uptick in these vulnerabilities related to regular expression denial of service attacks. They impacted CRuby, they impacted Rails, they impacted popular Ruby gems. If there was a vulnerability update for some key technology you used in 2021, odds are it was related to a regular expression denial of service attack. And I really do mean any key technology. This wasn't limited to Ruby. Now, Google Code isn't the best proxy, but if you look through the issues, it impacted languages with a regular expression engine like Ruby has. So there's a ton for like JavaScript, and if you still use Perl, that as well. How I kind of came into doing this talk was for completely unrelated reasons. I was working on regular expression performance for Truffle Ruby. With Truffle Ruby, we'd noticed that while Ruby regular expressions have a ton of functionality, In reality, many people use just a subset of that functionality, and we had a hypothesis that we could process those quicker than running it through like the full regular expression engine. So earlier in 2021, we had adopted this new engine that was based on a DFA, and I'll get into what that means. In particular, I was looking at performance on an open source gem we have called Browser Sniffer. Browser Sniffer makes it easier to work with user agent strings, so you can see like whether your users are on mobile or desktop, what browsers they're using. And I also looked at our primary web application at CRuby, at Shopify. And I found that in no instance did we actually use back references in regular expressions, which is kind of an advanced feature. At the same time, I was looking deeply at the CRuby regular expression engine to make sure that we maintain compatibility as we were looking to update here. Naturally, we wanted to see if the new engine was vulnerable. And in each instance, we found that no, the new engine in CRuby didn't suffer from these same problems. So, like in one example here, we ran with CRuby and the proof of concept took 22 seconds to run, whereas on CRuby it ran in 22 milliseconds. And this has nothing to do with like the way CRuby optimizes things. It's just because of this new type of engine, which is actually an old type of engine. So I'll get into that. So in order to understand what the regular expression denial of service attack is, we need to know what a denial of service attack is. This whole talk was like a really long setup for the 30th anniversary of Wayne's World. So that's what that no service is all about. So there's a lot to do like under the umbrella of computer security. Denial of service attacks are kind of the easiest one. No one's trying to like break into your system or do privilege escalation. They're really just looking to give you a really bad day. So the basic idea in a denial of service attack, particularly as it relates to Rails, is we have dynamic web applications. A user makes a request, we have a response. Presumably, we have some kind of performance target for those responses, whatever that is, 100 milliseconds, 150. But with the denial of service attack, those response times now go up into like the tens of seconds, or you get so flooded that you're unable to respond at all and the connection time's out. So you can have a denial of service where the attacker is doing something that just wastes a bunch of CPU, or they can do it by volume and just like flood you with requests, and that gets into distributed denial of service attacks. Some of this can be kind of contextual. Like, I think we've all accidentally had an N+1 query in our app, and if you have a small enough amount of data or your database isn't terribly loaded, you can get really far with that. But then suddenly you have a customer that has more data than you tested with, and now your requests take forever. So on this denial of service stuff, sometimes it can be difficult to tell whether it's malicious or just kind of coincidence, an oversight someplace. But with these regular expression denial of service attacks, generally you can tell they're being malicious. All right, so now that you know what the denial of service attack is, you might be wondering, okay, so what's this DoS stuff? So the first hit I got on Google was this definition from the Open Web Application Security Project. It says the regular expression denial of service is a denial of service attack that exploits the fact that most regular expression implementations may reach extreme situations that cause them to work very slowly, exponentially related to input size. All right, so that's kind of a dense definition. Let's go take a look at Wikipedia. They say a regular expression denial of service is an algorithmic complexity attack that produces a denial of service by providing a regular expression and/or an input that takes a long time to evaluate. I don't find that terribly helpful, so let's read the next sentence. The attack exploits the fact that many regular expression implementations have superlinear worst-case complexity on certain regex input pairs. The time taken can grow polynomially or exponentially in relation to the input size. All right, so it seems if we want to understand what a DoS is, we need to understand performance. So generally when we talk about performance, I think the first thing people think of are benchmarks. And benchmarks are nice. If we look at these charts, I didn't even have to explain it to you. You can tell there's different bars, they're different colors, they correspond to different data. Some are taller than others. Like, you don't know if that means it's better or worse, but very quickly, just looking at it, you can kind of tell how data relates to each other. Problem with benchmarks is they're notoriously difficult to replicate. If you even want a chance at doing that, you need the original code that was run and the inputs to reproduce it. But even then, they're very intimately tied to the system being run on. So like, for instance, if the benchmark was heavily multi-threaded, and it was run on a machine with 16 cores, and you're running on your laptop with 4 cores, you're gonna have wildly different results. Maybe the shape will work out the same, but you can't even rely on that. Another particularly pernicious issue is you really only want to be running the code you're benchmarking, but in modern systems, there's always something running in the background, and it's really tricky to normalize for that. So we'll try to work around it by running benchmarks repeatedly and doing statistical analysis on it, but even that gets kind of odd. There's like a whole field of study around how to reason about benchmarks this way. So those definitions of ReDOS that I went through look at performance via algorithmic complexity. All right, so algorithmic complexity, it's kind of an intimidating term. There are 2 words we don't use all that frequently in English. I think sometimes people come up with definitions that are a little more obtuse than they need to be. But the basic idea is instead of running code and measuring how long it takes to run, we reason about it and count some sort of key operation. And so for instance, if the problem you're trying to solve is you have 10 doors and 10 keys and need to match up each key with each door, how many times do you need to turn a key in order to pair them all up? And you can think of different ways how you might want to do this, and each strategy you can count how many times you need to turn it, and then you can reason about and compare them that way. So if you start with 10, okay, so that's one context. What if we made it now 20? Does the approach you originally planned still hold up? So with algorithmic complexity, there's always a context. We're talking about best case, worst case, average case, something else. The best case would be here, every key I picked up and put in the door worked on the first try. So I had to do 10 key turns, and that would be linear in size. In worst case, I pick up the wrong key every single time, and now I've done n squared key turns, essentially. So these operations, not only do we count them, but they're related to the input data. So if we were looking at like array sorting algorithms, how long that takes is very much tied to how big the array is. With regular expressions, the key input data is the size of the string we want to match against. So when we talk about algorithmic complexity, you might see this term asymptotic complexity. And this is where big O notation comes in. So going top to bottom, I went from like cheapest or fastest to most expensive. There's others that aren't on this list. But if you've ever heard someone say something runs in constant time or linear time, and they're trying to relate that back to big O, or maybe they say big O of n, like you just got to kind of have this mapping in your head. And you can have different algorithms that have the same complexity, but like the coefficients, or there's some kind of constant value that's off a little bit. With big O analysis, we don't really care about that stuff. We're looking more at the scale of it. So below this line here are the definitions that the Wikipedia page we're talking about. So we have big O of n squared, this is quadratic time. Big O of n cubed, that's cubic time. And collectively, this is polynomial time. We could keep increasing the exponent there. Below that, if the exponent is actually related to the input size, now we're into exponential time, and that's really problematic. So here's some graphs of what that looks like. This is where the term asymptotic comes from. So going top to bottom, left to right, it increases in how long it takes to perform stuff. When you get to the bottom, note that the scale changes. So even though the x-axis shows the same input size, by the time we get to linear rhythmic, now we're at the tens of operations. With quadratic, we're at hundreds of operations. And with exponential, we're at tens of thousands. So the growth is really big. You want to avoid that. One of the definitions referred to superlinear. They really just mean anything bigger than linear. So that'll be the stuff you see on the bottom row there. All right, so now that we know a little bit about algorithmic complexity, let's try to tie this back to an actual DoS example. I'm going to zip through this slide. I put this here just for reference. But what we're looking at is a regular expression that consists of n a question marks followed by n a's. I realize this is a bit obtuse. I use this instead of a real example from Ruby or Rails because Russ Cox has this really good article titled Regular Expression Matching Can Be Simple and Fast. And this is the example he uses in that article. So I wanted something that you could relate to after the talk. But yeah, so you'll have n, or count in this case, a question marks. And the question mark in regular expression syntax means it matches the a 0 or 1 times, followed by that count of a's. And then we're going to match it against that count of a's. So what should happen is all of those question marks should not match anything, and the match string will hit the back end of that regular expression. So I ran this with Ruby 3.1, and I kept bumping up the size of A. As I hit 36, it started taking 7 minutes to process. That was as far as I was willing to push it. Fun fact about regular expressions with Ruby, you can't interrupt them. So just got to wait it out or go ahead and kill that process. For those of you familiar with log scales, I plotted this out just so you could see that it really is exponential. All right, so let's turn to the regular expression part of DoS. So what are regular expressions? I think we all know what regular expressions are. In Ruby, they're used far more frequently than they are in most other languages because Ruby has a literal syntax for it. And then the Ruby core library allows you to supply regular expressions for a lot of things. In contrast, they're really awkward to use in C or in Java, so they're not used all that frequently. But regular expressions really are a DSL for writing a little program. So if you use regular expressions, you're a polyglot programmer. But if you think about it, you take this pattern string, you feed it into a regular expression engine, and what you get back is a little program that all it can do is match against strings. But then you can provide it input, the string you want to match against, and you get output that either says, yes, there's a match, or no. Or if you're trying to capture values, the match positions as well. Another way of looking at regular expressions is they're a set of instructions for building a state machine for processing these input strings. And that's the one we're going to dig into a little bit. And the more technical definition has to do with regular expressions describing this thing called a regular language. I'm not going to get into that, but if you're interested in the topic, I encourage you to go look into it. The reason I raise it here is Ruby and some other languages actually don't strictly match regular languages. They added some extensions, like being able to do back references that allow them to match things that aren't strictly regular languages. And this extra functionality is actually where this performance trap comes in. All right, so we're going to look at machines. Here are some machines from the 80s. A state machine, again, if you've never seen these terms, I'm sorry, they're terrible. But a state machine is an abstraction for encoding the state of a system or a subject. So if we look at a traffic light can only have one color active at any given time. So in a state machine, these states are represented by circles. We call them nodes. And then you can transition from one state to another by following these directional arrows. So at least in the US, a green light can only ever become yellow. A yellow light can only ever become red, and a red light can only become green. And this can run, I guess, as long as the light has electricity. So that can run forever. Sometimes transitions are conditional, so they'll have a label on it, and we'll see that with regular expression state machines. All right, so regex state machines, they come in two types, NFAs and DFAs. And I'm sorry, it's kind of terminology heavy, but if you ever look into what regular expressions do, you're going to see these terms, so I kind of wanted to just hit them quickly so at least you won't be shocked the next time you see it. So NFA stands for non-deterministic finite automata. Automata is just a fancy way of saying state machine. They're finite because we don't have infinite length strings. So when you take a regular expression you built up from a pattern and match it against a string, if you allow it to run long enough, you will always get an answer. And corresponding, like complementing NFAs, we have DFAs. These are deterministic finite automata. The big difference is with a DFA, for any given state, you can only ever transition to another state, whereas with NFAs, it's possible to transition to multiple states on the same input character. So going back to the example pattern from the Russ Cox article, here's a pattern with 2 A question marks followed by 2 A's. And we can see with the NFA, we could transition from the start to 3 different states based on the first A we see. And if you follow from start to S1, S2 to S3 to S4, then it matches all 4 A's. If you go start to S2, then it matches 3 of them, and so on. Whereas with the DFA, we transition from start to S1, and then S1 to S2, and if we ever see anything that isn't an A, we loop back around and just kind of reset the machine. I left the not A stuff off the NFA because the chart gets way complicated at that point. All right, so with an NFA, the question really is which transition do we take? And the answer is it kind of doesn't matter, other than when people run code, they expect to get the same answer on the same inputs. So the solution that Ruby and other regular expressions use is greed. So they're going to go try and match as many characters as they can on the first try. And if they fail, they do this process called backtracking, where they pretend they didn't match against the last character, put it back on the input string, and then resume the machine from this new position. Here's an example of backtracking in action. This little debugger thing comes from a site called Regex101.com. And we can see the matching process in action. Every time there's a red arrow, it's reached the end of the input and rolling back and trying again. At the bottom, we have the match string, so it's the thing with the blue. And every time we hit the red, that's how many steps it's backing up. So the match string is 9 characters. We're already at 100 steps into this process, and it will go for much longer. And this right here is the exponential issue that we're trying to avoid. In contrast with the DFA, you can only you only visit each character in the input string once. So as an example, if we're looking at the string AA, we transition from start to S1 on the first A, and then from S1 to S2 in the next A. The input string's done. We haven't reached a success state, so we're done. If you took ABC, you would transition from start to S1 on the first A, then S1 back to start because B is not A, and then you stay there because C is also not A. So what's nice about DFAs is they're always linear. It doesn't matter what the string is. You will never do more transitions than you have characters. So yes, if you give it a larger match string, it will get slightly slower, but it won't get exponentially slower. So rerunning that Russ Cox benchmark, where I went up to 36 characters, there's 2 implementations here. We still see that exponential growth with CRuby, but way at the bottom is a red line where I ran it with TruffleRuby and its DFA-based engine. And if we look at the logarithmic charts again, you can see that, yes, TruffleRuby is actually doing something, but as we increase the length, it just gets incrementally slower. All right, so like I said, I just want to make clear that NFAs and DFAs are, strictly speaking, equally expressive. So this backtracking stuff doesn't have to do with it being an NFA. There's no reason that the Ruby regular expression engine couldn't avoid backtracking when a pattern doesn't call for it. Just as a matter of practicality, that would grossly complicate the engine, so it's not done. So what we do in TruffleRuby is we use this DFA-based one, but if we have a pattern that doesn't match, we actually switch the regular expression engine we're working with and kind of fall back to something that runs more closely to CRuby's. All right, so how are we affected? So we write Rails applications. They're dynamic, so presumably we handle some sort of input from the user. Whether this is a form submission or an API call, we're allowing people to provide data to us. Alternatively, we could be using an API and sourcing data from someplace else, and we don't have control over that data set, so that data could be problematic. So how do we avoid these regular expression denial of service attacks? First off, never ever allow someone to give you a string that you build a regular expression from. I have seen this done, and it works okay if you have people that aren't trying to mess you up, but they can trivially give you a regular expression that'll run in exponential time. So the far more likely situation is you have a regular expression and that you want to match data from somebody else for, whether that's because you want to do some sort of validation on it or you're trying to extract components of that input string out. So one thing you can do is just truncate it, and you can't rely on front-end validation for this. Like, yes, you could have a form field and you can set the max length on it, but someone that is deliberately trying to mess you up can very easily circumvent that. So on the back end, you're going to have to truncate it or what have you. This is actually what CRuby did when it turned out that date parsing was problematic. So you can give it as large of a string as you want, but it'll only consider the first 128 characters by default. Upgrade Ruby and Rails when these CVEs come out. Both projects are very responsive, so they'll push out new releases that address any regular expression denial of service attacks that they come up. Attackers have a slight advantage with us because we're using open source technologies. So while you never want obscurity to be your only defense, all the regular expressions used in Rails and Ruby are publicly available. So attackers have a very easy way of reasonably knowing what you're running. So there's ongoing work to detect which of these are exploitable and addressing them. Ruby 3.2, which isn't out yet, adds a new mechanism where you can specify timeout limits on how long a regular expression will run. And you can do this either globally or on a per regex basis. Now that you know what a regular expression denial of service attack is and how you end up in this situation where things run in exponential time, try to think a bit more like an attacker. There's a lot of different ways to write patterns that will do essentially the same thing. So if you're able to, you should avoid things like nested quantifiers or avoid using the star or plus method if you really have an upper bound on how many times something can repeat. If you do groups, you can use atomic grouping to help reduce some of the backtracking. But yeah, just think through your pathological cases. Understand that because the problem is exponential, you're not really going to see a performance issue if your string you're matching against is only 10 characters. You might need to bump up to 100, and you might think, well, no one's ever going to do that, and then someone will do that, and you're going to have a really bad day. It's a little tricky because if the string were to match with either engine approach, it's not going to take that long. So it's not just the length of the input string, you also need something that's going to trigger all of this backtracking. And that gets a little trickier to think about. You have to look at the pattern and see what they're matching against, and as you formulate your test strings, you need to adapt them for a particular pattern. All right, I think we made it. There was a lot to go through. I'm hoping this was helpful. So I'm sure some of you have done algorithmic complexity before, but for those that haven't, now you have a new way of talking about performance that doesn't involve benchmarking. And as you look at established algorithms, there's typically some sort of big O notation attached to it to tell you how long it'll run. And I'm hoping this will help you better understand that. I hope we peeled back some of the kind of mystery around what a regular expression engine's doing. And by better knowing what's going on, you can hopefully better guard against these DoS attacks. Yeah, so then I've got some helpful resources. I'm not going to go through these. They'll just be in the slides if I put them up. And some educational resources This is the Russ Cox articles I was referring to. If you want to kind of get a deeper look at what a regex engine does, Kevin Newton, who I work with, created a regular expression engine in Ruby, which makes it really easy to look at. This was a Shopify Hack Days project, so you can check that out. T-regex is the regular expression engine used in Truffle Ruby, so you can see what a DFA-based engine would do. And yeah, thank you for your time.